Possiamo...
Certo.
Okay, so welcome everybody, thanks to be here, a lot of people. So in these two meetings I will, so there will be another meeting also next Monday, and these two meetings I will give an overview on the interplay between algebraic geometry and integrable system, especially with the discrete integrable system. So today I will mostly talk about algebraic entropy, but already the object and the tools that I will introduce will be useful to talk about the Painlevé equation next time. Okay, so let me introduce the algebraic entropy. So the first thing, so the input is a birational map of the projective space. And we know that in order to give a birational map is the same, so to give a birational map is the same as to give, it's the same as to give n plus 1 homogeneous polynomial of the same degree. So in this setting, one can define what is the topological degree of the algebraic degree. Depending, there is a lot of names that gives the same information. So Arnold used to call this a topological degree, which is just you take a line inside Pn, and you consider the degree of the image of the line. So of course, when I say in Pn outside from the indeterminacy of the map. So what do I mean by degree of the line? This is just the cardinality, if you want, of the intersection of H and phi L, where H is a generic ideal plane. So if you want, in a sense, this degree computes the complexity of the map. So how much a map takes a straight line into something of higher degree. But if you want to go down to the earth, how to compute this degree is very easy. So the degree, so this is by definition the degree of phi, by the degree of phi. So by definition, the degree of phi is just the degree of any of the entries of the map. We know that all the entries have the same degree, so this is the definition of the topological degree of algebraic degree. It has many names in the literature. So this is not the cardinality of the generic fiber of the map. Phi is just, so there is also this ambiguity in the terminology. It's just a way of measuring the complexity of the map. And how to actually understand how the map is complete. So we want some integrable system going on, and what we do is we iterate the map and we look at the growth of this degree. So the kth degree, so the degree, so is a definition. The kth degree, let me say the kth degree, because in a second I will change the terminology, but let me say the kth degree. Of phi is just the degree of the kth iteration of phi. And the easy observation here is that, of course, observation, the number d phi k is always smaller or equal than the number d phi to the k. So if I iterate, this number tends to increase. But in general, we have strict inequality. So the classical example which we will be interested in today is the standard Cremona transformation. So this is just the map defined by Pn to Pn. Cn sending xi to 1 over xi, which in other words is just x0, xi excluded xn. So probably I should have pi from 0 to n, and from 0 to n. So these two ways of writing the Cremona transformation are of course equivalent, because if I multiply all the entries by the product of all the variables, I get this way of writing. And depending on the kind of computation you want to perform, maybe this form is more suitable or this one is more suitable. For instance, just looking at this version of the map is immediate that the map is an involution, right? Because I take every variable to each inverse, and so if I iterate again this map, I get the identity. And so in particular what I get is that the kth degree of the Cremona transformation is n if k is odd. Indeed, as you can see, I have n entries, so the degree of the entry is n, and 1 otherwise. So in this example, the degree is periodic. Okay? And in particular, one can give a definition in this setting, and we say that the definition, the map phi is linear, quadratic, and so on if the growth of is, or similarly, the map phi is periodic if the degree. So I'm not saying that the map is periodic if the map is periodic, but if the degree. In general, in this case the map is periodic, but in general you might have a periodic degree, but not periodic map. Okay? So to work directly with the degree is not good, because this is of course invariant by conjugation by projectivities, but not by birational maps. So we want something that preserves, that is stable under conjugation by birational map, and this is precisely the algebraic entropy. So definition, the algebraic entropy as phi is just the limit as n tending to infinity of 1 over n, the logarithm. N was the dimension, sorry, so it's better. It's better to put phi. Okay. So the first question is does this number exist? So can this be infinite? And of course no, because the trivial observation is that this number is always smaller or equal than the logarithm of the phi, because of this observation there. So as phi is always smaller or equal than the logarithm. Phi. So in particular this is by Teorema dei Carabinieri, the comparison theorem that this always exists, because it's non-negative and smaller than a positive number, finite positive number. And again, as I told you, this is stable under conjugation by birational maps. And this is the tool that we use to understand, to declare if a map is integrable or not. So the definition is that phi is integrable with respect to n. I'm stressing with respect to because I will give also today, but mostly next time, a different notion of integrability. So with respect to algebraic entropy, if the algebraic entropy is 0. So for instance, the Cremona transformation, I mean linear, quadratic, all these kind of phi are integrable because they are polynomial, the growth is polynomial, so it's scaled by the logarithm. But in general, there might be maps which have exponential growth, and so in that case we don't have integrability. So the idea to study integrability, and so the way in which the relation between algebraic geometry and integrable system takes place is to construct something called the space of initial conditions. So there will be at some point some birational geometry construction going on, and yes, so maybe at the moment this is what I want to say about the relation. So this will be clear in what follows. Okay. Any question? Good.
Is this invariant under bilateral conjugation?
Yes, this is, but the degree growth is not.
Okay.
Yeah.
So it's really important that you
Yes, exactly. Because after all, we want to work in this category.
Yes.
So
yeah, no, that is what I thought. That this anyway wasn't going to work.
Yeah.
And then, but the point is, this does.
Yes, this does. Okay, so I want to spend a very few words about the Cremona transformation in degree 3. I'll say also something that is not very useful in the context of the seminar of today.
S5 is the algebraic entropy, right?
Yes, algebraic entropy.
Why equal entropy?
Because of the formula, I think. Yes, because of the formula here. This is the formula of the usual, the common formula for entropy. Somehow, if you look just at the growth of the degree, you get infinite. So you want to measure how complex is the map. So you want some entropy measures how complex is something. And somehow this does, no? Because it tells you how fast it's going to infinity. Usually this degree goes to infinity. So if you just look at the limit of the degree as k tends to infinity, you get infinite. So it's infinite for every sequence. But here you are understanding if the growth is polynomial or exponential. So somehow entropy in this sense, measuring how complex is the system.
So it's not related to probability distribution, the entropy of probability distribution.
No, it's not related to that. Everything here is discrete, so probably if there is a way to translate from the discrete. The problem here, this is also very important. In integrability, at least in this sense, is not well preserved under discretization if you start from something continuous or continuous approximations. So it's really something peculiar of the discrete case, this one. And you will see the example will concern something coming from a continuous equation, the Euler top. And we see integrability in this setting for many maps, but there is no analog in the continuous setting. Okay, so I want to spend a few words on the Cremona transformation, again, not because it's strictly necessary for this talk, because we will perform a different construction, or still related with the Cremona transformation, but because it is a very useful, it is rich of geometry and of symmetries, and is a, I mean, in the spirit of this talk, it's going to be important to know what's going on. So, the Cremona transformation in dimension 3 is again the same thing as before. Let me just write it once again. Let me see if I really need to write it once again. No, I don't, so I will not. Okay. So, if you look at this expression, you immediately realize that the indeterminacies of this map is the coordinate tetrahedron, so the union of the coordinate lines. So the locus where the map is not defined is this tetrahedron here. Let me call this T. So just the union of the lines, not the faces as well. So if you want to solve the indeterminacy of this map, as usual, what you do, you look at the graph of the map. So these are the two projections. If you want, if you don't have the closure by definition, you put the closure as well. And then you identify this graph with the blow up with center the tetrahedron of the full space P3. So let me zoom on some points, some of these points here to see what's going on. So I want to describe this blow up in step for two reasons. First, because it's singular, of a kind of singularities that physicists usually like. And also because if you look in the literature, there is an error. So the equations are correct, but it's written that it's smooth, but it's not. So it's good also to have the, so if you look in the book by Algebraic, it's written that the object is smooth. But also by private conversation within is not. It's kind of clear that it's not. So let me draw a picture. I will explain this just via a picture. So I start by P3 with the tetrahedron here, and what I want to do is to zoom at some point. After all, the blow up is a local construction. So what I see locally is this. Okay? So the first step, in order to construct this variety here, is I blow up the origin here. So I get, this is a toric description if you want, but let me draw the picture and then I will explain. So this is a P2, this is a toric description, and these are P1 bundle over this affine patch of this P1 here, these P1s that you see here. Then what you do is you perform, if you want, let me say differently, you blow up with this, sorry, there's something, no, because my picture is wrong, sorry, I blown up too much. I blow up the origin, sorry, pardon, and I get this. Yes, sorry, I blow up twice. And now what I do, I blow up, now that I have separated the three lines, I blow up the three lines. So I can just skip the one picture here, and I get an hexagon. And now let's see. These lines here, which comes from the coordinate lines of this P2, are now of kind -1, -1, because they are complete intersection of this surface and the strict transform of this hyperplane here, and on this hyperplane this line is exceptional, and same thing on this surface, which is a derived after all. So this is a -1, -1 curve, and inside a threefold similar for this one and similar for this one, and I can contract them to conical points. So what I get is and these are conical points. And this, so if I call this map epsilon, the map that we care about is this one. So,
okay, I wrote the other direction.
Thank you. The map that we care about is this one. So in particular, first of all, this blow up has 12 conical points. This will be relevant for the end of the talk, but let me say this now because the description of the Cremona transformation I wanted to give now. So as 12 conical points, it is a combination of two blow-ups and a contraction. And the nice feature is that if you look at this level, on the first exceptional P2, we have a Cremona transformation of degree 2. The nice thing that you see a Cremona transformation inside the Cremona transformation. Okay, let me keep continuing describing this map, but I will give some information which is a bit more relevant to us today, which is about so we looked at the indeterminacies, and now we look at the loci which are contracted by the map and the fixed points. So let me also introduce some notation that I will need later. So first of all, notation. I will denote by E, E1, E2, and E3, E4. This is a bit uncommon, but for the purpose of today, I will use non E0, E3, but E0, E4 for the coordinate points. So coordinate points. And then I want to also give names to the fixed points of the map. So the fixed locus of the Cremona transformation, I will write it as the disjoint union of two sets, P union Q, where P is the set of points having odd number of -1, and Q is the set of points having even number of -1. So let me write it: 1, -1, -1, -1. -1, and Q is with even number. So 1, 1, -1, -1, 1, -1, 1, -1, 1, -1, -1, and 1, 1, 1. And let's say that this is again Q1, Q4, and this is P1, P4. Okay. Notice that, I didn't say, but this is the fixed locus, because if you take the map sending each entry to its inverse, doesn't change. So you get again 1 minus 1 minus 1 minus 1. So all these points are fixed, and there are 8 fixed points, and I'm just splitting them into sets. One are the fixed points having an odd number of signs, and the other is fixed points having an even number of signs. So this configuration of points, E union P union Q, is a very classical configuration in, I wouldn't say algebraic geometry, but classical geometry, and it is called the Reye configuration. So, remark, the set R E union P union Q is a Reye configuration. In a second, I'm going to give the definition of Reye configuration. I would like just to say that a configuration in the tree space or in the space usually is a configuration having a lot of automorphisms. This is going to be important because at this point I can kind of anticipate what's going on. So the idea is I will take automorphism of this set, so induced by projectivities, and I will compose them with the Cremona transformations. This will be my phi, and then I want to compute the algebraic entropy of phi for every automorphism of this set. Okay? Of course, if you have any question, please stop. So the definition of Reye configuration is here. R inside of P3, cardinality of R equal to 12 is a Reye configuration if there exists L set of lines, sequence of lines. So there exists 16 lines such that R L is a 12, 4, 16, 3 configuration. So what does it mean? It means that I have 12 points and 16 lines, and to each point there are 4 lines, and over each line there are 3 points. This is the notation for the configurations. And but there is a characterization by Hilbert of this. So if there exists a set of hyperplane H1, H12, hyperplanes, planes if you want, such that H is a 12-6 configuration. In a second I will also draw a picture, so the picture makes everything easier. But before to draw the picture, I would like just to remark another feature of this Reye configuration. So remark is that E, P, and Q define coordinates tetrahedron. So in particular, each of these set is what's the name? Is in general position. The point is that so we would expect the set of 12 elements to have no automorphism at all. So these are in a very special configuration. So this is the point, and also will be relevant at the very end. So let me draw a picture. Because really, all the points relies on using the fact that this system has a lot of symmetries to compute something which is integrable. So in the picture in a local chart is the following. Okay, so if we go on a chart, it makes sense to do on some of the coordinate charts. Indeed, I didn't specify the indices here, just P means sum of the P's, Q sum of the Q's. So the situation is the following. I have the coordinate cube, if you want. In a chart, what I see are points which have 3 entries, which are plus or minus 1. These are the points at infinity, of the coordinate points of the plane at infinity. And so you see immediately, no, that this is what we see in a local chart, because you forget about one of the entries and you see 3 plus or minus 1, while you see the coordinate points goes to the origin and go to the origin and the points at infinity. And the 16 lines are the following. So let's see. Some of the lines are already there, because the lines composing the cube are part of the configuration. But we have 4 lines, and 4 lines, so we have 12 lines here, so 4 are missed. And the 4 missed lines are the lines to the origin. Something like this, I hope it's correct. And now, as you can see, to every point I have 4 lines. And on every line, I have 3 points. For instance, on this line, I have this P, this Q, and this E. Okay? This is the configuration. Any question? Okay. Yes. So as you can see, there is a lot of geometry here. And the other thing is that the configuration by the characterization by Hilbert, the 12 planes are the planes that you can see. So the 6 planes composing the cube plus the symmetry hyperplanes of the cube. Of course, if you put this point at infinity, the symmetry hyperplanes of this cube became the faces of another cube, of course. So there is not just 3 tetrahedrons, but there are not just 3 tetrahedrons, but there are also 3 cubes, because this is the cube composed by the points P and Q, but also the points E and Q make a cube, and same thing for the other pair, where cube has a specific meaning that I'm not going to specify, explain, but still in this with this flavor of configuration. Okay. Good. So what we have done with Giorgio, this is joined with Giorgio Bubbiotti, sorry, I didn't write it. What we have done is to compose the automorphism of this set with the Cremona transformations. So let me first define what do I mean by automorphism of this set. Maybe I'll put the name of Giorgio in the definition. Myself, Bubbiotti. So the Cremona cubes group. Sorry for the name, I choose this name, but now I'm not so happy of that, but that's the name. Is C G N P G N, and such that for C such that G of R is contained in R. Well, of course, we know that contained means equal, because there are 12 points. And the theorem, the first theorem that we proved, is the following. First, which is very important, C acts on the set E, P, and Q. So this is very important. Why? As you can see over each line, it's not just that you have 3 points. You have 1 point coming from P, 1 point coming from Q, and 1 point coming from E. So since elements of PGL acts on lines, this C also acts on this set of 3 elements. So if one element of E is sent in an element of P, then all the elements of E are sent to P. Then the second thing is that the cardinality of this group is 576, and the third is that the third is done by computer, of course, is that this group is isomorphic to the alternating group for symbols. Times Z modulo Z, semi-direct Z modulo. This is done by gap. So there are a lot of, it's a computer system to work with groups, with finite groups. There is a huge database, so the group was already computed. I mean, you give the generator, you have to compute the generators.
Yes.
Then you give the generators and it tells you the isomorphic type of the group. Yes, so there are a lot of symmetries and this will play a role. Okay? And of course also this will play a role. Okay.
What's the name of the group again?
Cremona cubes group. Yeah, cubes, because there are at least 3 cubes. So maybe I can write the...
Do you have a geometric interpretation for this A4 squared Z2 and Z2?
No. I can partially answer, because yes, but I never sit down to investigate the relation with some, but I will tell you something later.
No,
Yeah. I have something to say, but not as the precise answer, because it's a mess.
I mean, maybe naive. So, what I understood so far, so we have this Cremona transformation of P3, and it has a point where it's not defined, so in order to make it honest transformation, we need to consider some block, some resolution, and it's to some extent defined.
Yes, exactly.
And then we somehow changed its subject and went to this honest geometry, not algebraic, just geometry, and finite groups, and this is theorem. And probably at some point this group will talk somehow with this block space.
Exactly. At some point we will perform a blow up, which is not going to be the same blow up. We're going to perform a different blow up to deal with this matter. Yes, because we will see that if you want to compute the algebraic entropy directly, this is kind of impossible because you should check all the iteration of the map. But there is a cohomological characterization of the algebraic entropy, which is given in terms of this roof that I draw, this roof diagram that I draw, that it will give you a way to compute the algebraic entropy without performing any infinite computation. So that's the point, using the geometry to avoid the infinite computation.
Yes, but computation is done on some resolution.
Yes, on some resolution, yes, which is called the space of initial condition.
Yes,
exactly. Okay, so the question is the following. Is to compute the algebraic entropy for phi of the form C3 composed G over phi of the form G composed C3. So one might complain now, why didn't you call this Cremona cubes group? Because this is not a group. So the collection of maps of this form doesn't form a group because this is not normal. The subgroup generated by the Cremona transformation is not normal inside the V of P3. And so it is not true that the
What is C3 here?
No, C3 is always the Cremona transformation.
What is G?
I see, for G, the name, for G.
Okay, and one of the two.
Yeah. For G, the Cremona cubes group. Yeah, so I was about to explain without writing. I want to compute the algebraic entropy for maps of this form, where this is the Cremona transformation, and G is an element of the Cremona cubes group.
So it's how do you call it, laterale?
Yes, this is a laterale. This is not, I don't know in English how to call it. This is not a subgroup of the group of the rational transformation. That's why at the end we just have we give a number. There are dot functions of this type, dot functions of this type. Okay. And a motivation and a remark, and then I move to the actual explanation. So the motivation for this specific example is that many maps come from discretization of continuous dynamical system already known. For instance, Euler top is of this form. So the KHK discretization of the Euler top is of this form. And since there is a lot of geometry and symmetries here, we expect to have to find other interesting integrable systems in this set.
KHK is some name?
Yes, Kan Hirota Kimura. Hirota Kimura. Just a fact, very in a second, because probably later I will discuss this. Notice that if you take 2 elements inside Q, then this generates a net of quadrics. So, first of all, this is going to be something understood as invariant, this set for our map, in a sense that I will specify later. And what I'm saying is that there is an invariant which is cut out, first of all, it's zero-dimensional, and this is cut out by quadrics. Notice that, so in particular, zero-dimensional here implies Calabi-Yau. Notice that if instead of having...
Sorry, what is Calabi-Yau?
It's trivial canonical band. It's just
zero
points.
dimensional.
Yes,
Yeah.
And instead, if you look at if the invariant locus, in a sense that I will specify later, is bigger, is for instance a curve, is cut out by 2 quadrics, and we get an elliptic curve. So again, something over which it makes...
Is it a net or a pencil?
In that case, it's a pencil.
In this case,
In this case, it's a net. In this case, it's a net, yes. In that case, it's a pencil, and you have a pencil that defines for you a curve, which is Calabi-Yau again, which is elliptic. And we will see that our result will split in 3 parts. One is the case in which the invariants are precisely this, the other in which you have elliptic curve. In the last case, something very strange happens, because usually in dimension 2, when you talk about integrability, you look for having enough invariant. So you want at least an elliptic curve or a bunch of points, 8 points usually. This will be more clear also in next talk. Just I want to say something in words. While here you have more room, and what's going to happen is that in the non-integrable case, we still are going to have invariants, just 1 quartic invariant, so again it's Calabi-Yau, but 1 invariant will be not enough to guarantee integrability. But I will say this later. This was just to say, to introduce something what will happen.
Sorry, what fact? What mean 2 point generates?
Yes, yes. This is a subset of. These are collection of points. I'm just saying that through this union, so these are 8 points.
Okay.
Through these 8 points, there is precisely 1 net of quadrics.
Is this 8 points?
Yes, 8 points, because these are, I'm saying just take 2 out of these 3 sets. Each of them has 4 elements. So
it's a very special set of 8 points, which is a complete intersection of 3 points.
Yes. Okay, so the algebraic part of the algebraic geometrical part of the story, which is the notion of algebraic stability. So, algebraic stability. So the first thing you need is a notion of pullback. So, suppose to have phi birational in x and y, wherever I'm not saying, but let me write at least once, x and y are projective and smooth. Actually, smooth is not really necessary, and I believe that because among the open question, I will say that this theory is not completely settled in dimension higher than 2, and I believe that one should drop this assumption in order to generalize this construction to higher dimension. I will explain why I believe this in higher dimension. But let me say that for the moment we just need the smooth because we work with P3. And so what we do is you take the graph of the map, graph of phi, you take the closure, and then you take a resolution of singularities so that it is smooth as well. And then you define your f and g, and you define the push forward of phi as the pullback via f composed with the push forward via g. And you define the pullback as the inverse of the push forward. And you can check that this is well defined because this map is birational. Okay? Great. So now.
On what pullback and push forward coherent sheaves or?
No, sorry, for line magnets. Sorry, because I want to pull back and push forward divisors. So yeah. On this is on really on if you want on H2 on H2 on here. This is important. Thank you. And we say that definition phi is algebraically stable if the end iteration of the push forward is the push forward of the end iteration. But immediately one characterizes this definition, and it seems why do we need to block stuff? It's clear why do we really need to block stuff. Yes?
The definition of pullback, the star on the right is bigger, right?
Yes, now we have a projective morphism between.
Phi minus 1 push forward.
Yes, 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 thank you, yes. Thank you.
So you iterate and you don't need y to be equal to x, they are different.
Now, yes, yes. Because then at the end it's always this way, yes, in order to iterate. It's a birational map actually, you can, with abuse of notation, avoid that, but yes. On an open subset it is an isomorphism, so you can keep going on that open subset. But
And what's
yes,
the end?
yes. Huh?
And what's the end? You mean
An
for all
iteration,
n?
for any end, for any end. You iterate and you want. Okay. I wanted to say another thing, maybe. No. So what is a space of initial condition? But I wanted to say another thing. What is? Here, okay. Fact, which is the fact that we care about, is the following. Phi is algebraically stable if and only if for every k in Z in greater or equal than 0, greater than 0, sorry, phi does not contract any divisor on So what's the point of a, yes?
You mean phi to the k does not control.
Yeah. So what's the point in algebraic stability? The point in algebraic stability is that if some divisor is sent to the indeterminacy locus, then you are not able to follow the iteration of the map, because you cannot apply the map on the image of the divisor. So the only thing you need in order to do the computation of the algebraic entropy, so instead of looking at the curve you look at the divisor, is to have a map which is not contracting any divisor in the indeterminacy locus. Once you have this, the mapping homology became an isomorphism. Okay? And you can compute the algebraic entropy. In a second I will say how to compute the algebraic entropy. This is just to have an idea. So the issue in general is that you are working with the second cohomology. Working with the second cohomology means two things. Two things can happen. Or your divisor never die, so never finish inside the indeterminacy locus. And in that case you can follow the iterations and understand how the degree changes. Or your divisor goes inside the indeterminacy locus and you miss the divisor. And so you cannot compute what the map would like to do. And how you perform then the computation if the map is not algebraically stable, you make it algebraically stable using blowouts. So now we are going to use blowouts. So the definition is that phi in B of Pm. So I take phi, then a space of initial conditions for phi. Maybe I want to say with respect to algebraic entropy, because next time there will be others. Is a birational morphism, birational projective morphism, epsilon from B to Pm, such that phi tilde and phi minus 1 tilde in B are algebraically stable. So, what you do, you blow up enough in order to make phi tilde and phi minus 1 algebraically stable. So, this is a birational morphism, so I can identify bir Pm with bir B. So every phi here, every birational map from Pm to Pm, lift to a birational map of phi tilde from B to B. Okay? And I'm requiring this map to be algebraically stable. Is it clear?
So what I don't read the squiggle, is there exist or
Where?
for phi is a space
Algebraic stable.
phi is a
No, phi, virgola, a space of initial condition is
okay,
a
sorry,
birational
now I'm confused. For phi in
Yes, take phi is an
Two
element.
separate sentences.
yeah, you know. It's
Yeah.
just, I understand saving, but you're
Yeah.
not really saving anything. A space of initial condition for phi, so you are defining a space
Yes,
of initial.
definition, I'm defining a space of initial
And the
condition.
space of initial condition is a morphism.
Is a morphism which is birational and projective, such that the source, the domain of the morphism, on the domain of the morphism,
And
you can
do you
define.
want to be smooth, projective?
Now the point is the following. The point is the following. I was about to say what I was saying about before. In the definition, all the definitions here, I have smooth. So you should complain, and indeed I should put here be smooth.
But you want it projective at least.
Yes.
Oh yeah, because it's projective.
Yeah, it's projective.
Yeah.
Yes, it's a projective morphism.
So this you don't want.
No, this I don't really need. And I put smooth. The point, what's the point? The point is that when you work at least with the threefold, this is really too strong. And this
Would
definition
you
was
want terminal?
I think terminal, because in the example that I'm studying now, which is in dimension 3, and the problem is not happens on points, I have a lot of, canonical in that case, but yes. No, because it's with conifold, I can put canonical in that specific case. In the general.
Conifold is terminal, right?
Yes,
So why canonical? There are more.
Sorry. The resolution is smooth and is terminal. I want canonical. I think that canonical is what you need, which is.
But divisors don't behave so well in canonical.
My one should rephrase a bit the theory, in my opinion.
Okay.
I don't think that the stuff in this way will work.
But on surfaces it's smooth.
On surface, you can take the minimal model project and everything work because you can
Yeah, but
define a
then if you
minimal.
take smooth in surfaces, you can take terminal.
Yeah, indeed. But smooth is enough for surfaces, but I don't believe that it is.
No, here no.
But there is no definition given in dimension 3 and higher. Indeed, we remarked this in our paper. It's a theory that already in dimension 3 has just some sporadic example. There is a not settled. In dimension 2, the theory is very well settled. All the integrable maps have quadratic growth and so on. But in dimension 3, no. It's not clear even which kind of growth behavior you can achieve. It's not clear. So I think that smooth is too much. In the example that I give today is enough because you will see, but no, you won't see because I spent all the time to explain this. But so let me give the statement. Let me just explain the statement. And so just 2 statements and then I stop. So the theorem which we use is by many people, but let me go to them because the speed of the paper is more near to ours. So we are left and independently Carstea as an hour. So the tool, because I didn't tell you how to compute the algebraic entropy, is the following. Take phi to be near PM and take a space of initial condition. Then you have a notion of push forward. So this is just a matrix between 2 lattices, and what we get is that what we look at the pullback of the coordinate hyperplane, and we send it forward. So, and now here we have the same basis as here. So you write this as some multiple of the coordinate hyperplane plus exceptional stuff. The point is that d phi n is precisely this alpha n. So now it's a problem of linear algebra to compute the algebraic entropy and the growth degree. Because you just have a matrix, a very specific matrix, and you want to see how the first entry increases under iteration. Indeed, now you know that the pullback of the empty iteration is the empty iteration of the pullback, and you get the result. So let me just state my result with the Giorgio, and then I will conclude. There are questions. So the point, everything relies on constructing via blow up, and I will say more next time, a space of initial conditions. Once you have a space of initial condition, now you have a problem of linear algebra over Z. And you solve it.
Are there any additional assumptions like B is smooth or maybe even to make?
No, B is smooth. No. They put B smooth. They use the definition that we give, which is this one. Of course, it might work. It's not an if and only if. It might work also in cases in which B is not smooth.
But
B is a space of initial condition, as smooth is in the definition of space of initial.
This error is the fact that B smooth, of course.
Yes. For smooth, the theory is settled. The point is that Are you sure that you are able to compute a space of initial condition which is smooth? That's the point. And what's the minimal construction that you need? So let me state the theorem, which is the following theorem. So again, myself and Giorgio Gubbiotti. So take phi equal to G composite C3 for G in the Cremonic group. Then you have three cases. Case 1, case A, the cardinality of G of the orbit of E. So I take the orbit of E and then I compute the cardinality is A. Then the degree growth is n squared. In particular, so this is for n tending to infinity. In particular, phi is integrable. And it has a covariant net of quadrics defining G. No, net of defining 8 points. B. If the cardinality is 4, then phi is periodic. No, sorry, defining, sorry, this is for the covariant. I told you about the invariant. An invariant pencil of quadrics defining an elliptic curve. Phi is periodic. And it has blah blah blah, a net of quadrics defining 8 points. C, if...
Sorry, when you say invariant, do you mean that each quadric is invariant or that depends?
No, invariant is that, invariant I mean the second. Not each quadric is invariant.
But
the pencil is invariant.
So you make it act on pencil of quadrics and exactly one is invariant.
Exactly.
And here, of course, in some sense, you still make it act on pencil of quadrics and the pencil of quadrics which are, but you don't have an invariant, but the invariant is a net.
Yes. So how do you do this? Simply, you take the quadrics through these 8 points and they will pass through 2 other points. And so you look at the action on the 2 other points and this gives you the invariant one. The case C, you have that if the cardinality is the whole group, then we have that phi is the logarithm of phi square, where this is the golden ratio. And in particular, this is positive, so non-integrable.
This is S phi, right?
S phi, yes, thank you. And but in this case, we have one invariant, which is a desmic surface, desmic quartic surface. And this is just, if you don't know what a desmic surface is, you just take an elliptic curve, multiply by itself, you go to the Kummer, you can go to the Kummer, or you have another contraction where you contract 12 lines instead. The Kummer you contract 16 lines, you have another contraction on our invariant surface F, and you have another contraction when you contract over 12 A1 points, your 12 of the lines. So these are going to be the quartics having a node precise. This is going to be the quartic having a node precisely at the 12 points. So there is a pencil of them for each map, one is invariant. To conclude, the very last thing that I want to say is that this was easy because the way in which the group was acting on the meaningful subvarieties of Pn was moving points. So these are finite sets. What the construction that we are looking at now, I just draw a picture, is the following. You have all these 4 tetrahedron, just draw them maybe, and then you have other tetrahedrons, and the intersections of the 2 by 2 of these tetrahedrons gives another Reye configuration at prime, and now you have 2 Reye configurations and an involution sending one to the other. So you can increase the group and look at the symmetries of this set, in this setting here. The point is that now you have these bad points here, and when you try to make the map algebraically stable, you get singularities. You get a lot of singularities. And even though the map is not working on line bundles, it's working on cycles. So you can look what happens on cycles, because obviously...
so you replace that H upper 2 with an A upper 1.
Exactly, because, indeed, just to conclude, because what you have is all the singularities will be of conical type, so they admit a small resolution. So actually the theory is done in codimension 2, and the theory of cycle doesn't see codimension. The theory of 2 cycles doesn't see codimension 2. And that's why you can work at least here still in the singular and in non-singular setting, but in general you cannot expect to work always in the smooth setting. So it's okay, and I conclude here. Thank you.
So just to see the connection. So do you use this theory of these system of initial conditions in your theorem in the end?
Yes, yes. What we do is we build a space of initial condition, and then we compute this map here, the matrix. And then with some methods of linear algebra, we are able to compute
So do you give a version of this theorem up there in general as well? Or?
But we manage to work in the smooth setting because since all the loci we have to blow up at points, distinct points, we don't really never find something which is singular.
So does the space of initial conditions always exist?
And that's the point. Dimension higher than 2 is not clear.
Ah, okay.
That's the point. Smooth, I think not.
No, beyond smooth, but...
So in that case always exists because you can always take the graph of the map. So if the map is solved, so if you don't have indeterminacies, then you always have the space. So in this sense exists also smooth because you can take a... Yeah, but it's going to be something enormous and you won't have any control.
Ah, okay, so in some sense you want a minimal space of initial
you want to do the computation. At the end you want the answer. If the map is not just that exists, then you want to do the computation and you want to know how the algebraic entropy. So for instance here there is this logarithm of the golden ratio square, which is there was some relation between the entries of the map.
Can you give some announcement of the next talk?
Yes, so about the next talk I will still talk about the spaces of initial conditions, but in the Painlevé context. So the idea is that I will recall, because it's a huge subject, the ideas by Okamoto and Sakai. And what they did, especially Okamoto, the work by Okamoto is more handable, so this is in the continuous setting and this is in the discrete setting. So what they do is, at least for surfaces, they have this very of points where a map is not defined, and they build a space of initial conditions for this map, and they realize something very similar to Mackay correspondence for people from algebraic geometry. So they manage to classify Painlevé equations according with the configuration of -2 lines in the space of initial conditions. which is precisely McKay correspondence. There is an ADE configuration of -2 lines, and from there they were able to classify Painlevé equations. And this is solved in dimension 2. This is very clear. This is a bit more intricate just because we have much more cases, but in dimension 3 is completely an open problem if the configuration of the exceptional locus can determine the Painlevé property for a differential equation. One of the experts that I know is Alexander Stokes, and we are trying to do something on this direction, but really very sporadic. So working on examples so to get some idea on how it should work. And it's very complicated.